Hello, welcome back to this series. We are trying to write an operating system from scratch, and we are still writing our bootloader. So today we will tackle the challenging part of this first stage of the bootloader, which is loading the second stage from disk. Let's get started. This is the game plan. So we want to read from disk. So things we need to know is that the BIOS puts the boot drive ID into DL. And also we need to know that for hard drives, the first hard drive will be 80. For the first part, we've loaded our bootloader into a floppy, but that's something that we will try to change because I don't know for you, but I don't have access to any floppy reader anymore. So yeah, we will be using hard drives. A USB flash drive is a hard drive if you boot from it. So if we want to run this on an actual machine, we can actually burn it into a USB drive and just boot from it on the machine. So what we'll assume is that we will be booting from some sort of hard drive. That's the point here. Right, so we have the ID of the hard drive starting with 80 in DL. And we will be using quote-unquote modern BIOS extensions, these two here. 13H is the interrupt, and extension, the function name on the interrupt is 41 and 42, which are the extended read and check extensions. So 41 is check extensions and 42 is read. There's also a 43, which is the extended write, but we will not be using that for now. So that's the game plan to read from disk, and let's go back to our code. So this is the code that we've had last time. We just printed hello world in a loop. All right, before we start working on reading from disk, I want to do a few changes, a few quality of life changes. I find that doing this move si and then call the print function very tedious. So what I want to do is I want to simplify the use of this print func, and the way I will do that is I will create a macro. The macro will be called print, and it will take a single argument, which will be the message. And so what are we going to do here? Okay, so if not message equals si, so if we didn't call print with si, means that we want to save what's in si on the stack, then move, basically do this. So if we don't already have the message in si, we want to move the message onto si, right? So si, move message into si, and then what we want to do is do the second thing, call print func, and then we need to restore si. So same condition here, and if, and we just pop si, right? So basically here we are assuming that we have a functional stack, which we still haven't set up, but we will need it for to read from this. So it will all come together in a bit. So yeah, let's check this. Does this build? Yeah, it does build, so it's good. Cool. So what I want also is I want another method that will let me print error messages and then halt the execution. So panic func. So what do we do here? So what we need to do is read a keyword. Well, actually, before we do the keyplace, we actually need to just call our print macro with our error, which will be SI, right? And the way I know it's SI is that in the usage here, we just assume that the string would already be in SI. What we can also do is we can print a sort of prefix error message. So let's call it panic prefix. And we'll try to add that somewhere here. Panic prefix. That would be something like what would be a good panic prefix? Let's call it boot panic. Something like this. Okay. Looks good. Right, so we print the prefix and then we print the whatever message is in SI, right? And the way we use this print macro means that SI gets restored here, so we can reuse it here. It should be fine. Then what we need to do is we need to read from keyboard, and the way we can do that is actually using this int 16.0 wait for key press and read character. We don't care about the read character part of it, but wait for key press is where it's at. So what it needs to have as input is AH as 0, which is this part here, and then we call the int16. All right, let's do that. So actually, instead of just saying AH to 0, let's just use just XOR the whole AX register, since we don't actually need AL for anything. And then we can obviously call int16h, right? Is there something I'm missing? No, we should be fine. Okay, and then what we need to do is we know that the first instruction, the BIOS executes, is at the lower byte of the first megabyte, right? It's here. So, oops, sorry. So what we need to do is, if we force the execution to hit this instruction will redirect us into the post routine, and by doing that, we will actually effectively have reset the VM. So let's do that. Let's jump far. We'll get into why we're using far some other time, but just trust me on this, and let's do it this way, because we need to jump far and we need to address a code segment that we are not in currently. We cannot reach from where we are. Okay, cool. So let's try to build it. Okay, it's not working for some reason. Reserved word used as symbol. Oh, of course. Yeah, my bad. Good. It's built. It should be fine. So now if I go here and just try to panic func move si hello. Do we still have the hello? Yep, we still have the hello. So we will want to print hello and the as the panic message. Let's build this. It's fine. Let's run it. Okay, great success. So boot panic, which is our prefix, and then the error message, and then now it's waiting for our keyboard input. Right, so now let's go into the actual thing that we wanted to do, right? We actually wanted to read from disk. So what's the game plan here? So to read from disk, we know, actually something that we need to know is that the BIOS puts in DL the ID of the boot drive. So the drive we're booting from goes into DL. When the boot drive is a hard drive, and by hard drive I mean anything that's that can be emulated as a hard drive. So hard drives do start at ID 80, which means that the first hard drive will be 80. We'll be using modern BIOS extensions to read from disk. So we'll be using the same interrupt, which is 13H, which is the disk interrupt services. We need to go here to the Wikipedia page on the 13H interrupt, which basically gives both the old extensions and the newer ones. So here we have 02, which is the old extensions that we have here, read disk sectors. But we also have 42, which is the one we'll be using, which is the more modern one. We also have the 41, which is the check extension present, which basically will let us check that we can use this 42 or not extension. I think it's not, yeah, it was a bit too small. So, but anyway, the links will all be in the description, so you can follow along. Right. So what we want to do, actually the last thing on our game plan I forgot to mention is that we will be using LBA packet structure. LBA is short for logical block address, and this logical block address basically is a way for us to not think about how the actual drive underneath us works, and we'll just assume that the drive is a contiguous list of sectors. So we will have sectors 0, 1, 2, 3, etc. until the last sector. We'll be using this logical block address packet structure because we want to write an operating system and not just a bootloader. So we need to simplify things for ourselves. Right. So let's start by removing this thing here. And let's just add a label to indicate where we're going to start. And let's just do stuff. Okay, so first thing I want to do is I actually want to save the boot drive ID, right? Okay, so let me just get rid of these things. Yeah, should be fine. Error messages, go here. Padding and boot signature goes there, and then variables. I guess I can call them variables. They can go there, right? So first thing I want to do is I want to save the boot drive ID. So we know that it's a single byte and it's in DL. So let's just call it boot drive and actually do something like this. We'll initialize it as 0. And actually, hold on, let me just, oops, there we go. So let's initialize it as 0 and Yeah, I guess that's fine. And then we just need to go and start working on our stuff. So first thing I'll do is I'll move into boot drive. I guess that's how I called it. DL, right? The byte in DL. Actually, I need to, yeah. So let me just tell it that it's a byte pointer, so it just copies a single byte. Right. So and then we will check that we are running from a hard drive, and this is where things get dicey, because once we are done with this code, we will not be able to run it straight away from on box, for the very simple reason that until now we were running on a floppy, and floppies don't need partitions, whereas hard drives do. And since we haven't yet defined any partition system for our hard drive image, we actually don't have any hard drive image at all. So that's that. That means that we will not be able to boot from a hard drive for now. So what we'll need to do is, once we are done with this code here, the next step will be to write some utilities that will make it easier for us to create hard drive images and load them with our kernel, and write the bootloader onto the first sector so they can be loaded and executed. Right, so let's continue. So we want to check that the DL is, so we want to compare it to 80, which is basically the first hard drive. So all other hard drives will have at least 80 as their ID, which means that if we are lower than 80, we are not booting from a hard drive. So we will need to panic. We will need to do something else. So what we want to do is, if it's lower, okay, I want to jump to some other place, which I will call not HDD, okay? And we'll just set up that not HDD, actually not HDD here, right? Okay, so if we have, let's add another HDD found, or actually let's call it is HDD. And so now we know that we are running from a hard drive, right? So what we need to do is we need to check if our hard drive actually supports to be addressed in the LBA addressing scheme. The way we do that is, hold on, let me just bring up the browser again and bring up this thing here, which is the 13H41 extension, check extensions present function. It takes, the parameter it takes is that in AH it needs 41, so that's a given. In DL it needs the drive index, and here they re-say that the first hard drive needs to be 80. And in BX we need to set this constant here, which is basically the boot signature. And the result of this function here is in the carry flag. The carry flag will be set on, so it will be set to 1 if not present, and it will be clear if present. Okay, cool. AH will be another code or a major version. BX will be basically the same thing we've given it, but inverted. So that's something that we might want to check to see that it went well. And the thing that interests us is that in CX we have as a bits on the word in CX. We have bit 1 is device access using the packet structure, which is what we want. So we can access this device using the LBA packet structure. 2 is the drive supports locking and ejecting, which is basically something that's for CD-ROM players and stuff like that. We don't care about this. And 4 is that we have enhanced disk drive support, EDD, which is not something that we do care about for now. So what we want to do is we want to call this function here, 41. We want to check that we got the correct results. And we want to check that we have this bit set in CX. And once we do that, that means that we are good to go to actually use LBA addressing or the LBA packet to read from the drive. Okay, let's go back to code. And what we want to do here is we want to set up our checks or our calls to 13H41. So let me just go ahead and copy this from Wikipedia and just put it here. Right, hold on. There we go. So these are the things we need to have set up. So let's start by working on these. So let's move into AH41H, right? Then we'll need to move into BX, the word we have here. Right, so let's just put a... it should be, actually, we just need to tell that it's a word so that it doesn't do funny stuff. Actually, I need to start putting the sizes in front of the operand so that it doesn't do funny stuff. Right, so what we need to do now is very simple. We just need to call our interrupt. So do we have... Yep, so in DL we already have the drive byte. In AH we have 41, BX we have the thing. Cool. So now that we have the results, we first need to do, let's copy the results. Let me just copy them from Wikipedia very quickly. Right, so let's just do it like this. Actually, this one here, I don't know if it's... I mean, if we don't have this and this, that means that we have an error. And instead of having the error code, I guess we can just print a custom message. Yeah, so let's do that. All right, first of all, we need to check the carry flag. We have a conditional jump that basically is jump if carry. And we know that the carry is set to 1 if it's not present. So if we have this jump to carry, that means that we fail. We do not support the LBA. And actually, let me just add not LBA. Okay, I'll add another label here, same as not hard drive, but it's called not LBA, and we'll be jumping there. Okay, so not LBA. If we don't have if we have the carry, actually, if the carry is present, that means we don't have the extensions, so we move on, right? Otherwise, we need to check. So we need to compare BX with what we expect it to be, which is this. And since the first one is not a number, I need to do something like this. And if that fails, so if not equal, again, it's a jump if not equal, I'll just jump back to, or jump to the same error point, I guess I've created, label error, or error label I've created. And the last thing I want to check is Actually, yeah, I forgot to copy this part here. Here we go. And I guess, oops. There we go. Right, cool. So, oops. No, that's not what I want to do. There we go. So, bit 1 means device access. Right, so let's just check. So, test CL, we basically test it with just one, right? So what this basically does is it does a and then a compare, right? But since this pattern here is used a lot, we have this test instruction for it. So if it's not 0, this instruction sets the 0 flag. So 0 flag is the same as the carry flag. It's another flag. If the test fails, the 0 flag is set. Yeah. So we want to check that it's not set. So jump if not 0, and if not 0, we will jump to I guess LBA. Okay, and that will be somewhere here. LBA, okay. All right, so basically what we'll do is, if we fail at any point here, either this part here, or this part here, or this part here, well, not this part, but this part here, or this part here, we'll be jumping down to this point. Otherwise, we'll just jump over it and go to this LBA, okay. And let's write these this point here. So what we want to do is we want to panic, right? So we want to move SI some error message. I guess we'll call it LBA not found or something. Actually, let's let's split these two messages. We might have an issue with the size afterwards because as we've already discussed, we only have one sector to write the full code to load from disk. So if we ever have a size issue and it doesn't fit into one sector, what we can do is we can come back and trim the error messages, and if that doesn't suffice, we can just try to merge together the error blocks to have just generic errors instead of an error per block, right? So let's move LBA not found, and since we actually don't want to come back here, so we will not be using the call, we will be using the jump, and we will jump into the panic func, right? Is that how I've called it, if I still remember? Yep, cool. Actually, yeah, that's I don't think it makes sense since the panic to use call, since the panic func uses jump far. That means that we do not really intend to go back to use a ret to go back to the caller. So it was an oversight on my part. But yeah, I guess we'll be calling it with a jump instead of a call. Right, so I'll just copy this, go over here, and here we need to do not hard drive, right? Let's create those error messages. So LBA not found would be something like, of course, not forget the 0, and then not HDD, right? Not a valid hard hard drive. Hard drive doesn't support LBA. Struct. Right, cool. Cool. So here we have basically panicked on error. And what we need to do now is we actually need to start thinking about reading the disks into, rather sectors into disk. So what we will need to do is actually, thing I forgot about is we'll need to come all the way here and set up a stack, because we want to use the print macro that we are using in the dpanic function, and we want to use the stack. The main question here is, where do we set a stack? And for that, I think we have a, where was it? Where is the memory map? Right, so let's bring this up. Right, this should be fine, right? Okay, so what this memory map tells us is that in real mode space, so on the first megabyte of memory, the memory is more or less normalized. The memory usage, I mean, it's more or less normalized. It means that we have kind of zones that are off limit, that are unusable, and we have some zones that we can use to our discretion, and we have some zones that are used by the BIOS, some other zones that are used by the video display and stuff like that, right? So what we need to do is we need to set up a stack. So we need to find a bit of memory that we can we don't need much memory. We just need about 256 bytes or something, starting from 0x500 all the way to 7FFFF. We have about 480, 500 kilobytes of memory, more or less. That's usable. So the bootloader just loads us here at 7C00, but that doesn't mean that we only need to use memory from 7C00. That means we can also look back and use memory from earlier if we want to, because there's quite a bit of memory back there. And what we also can do, if we wanted to, is here we are in the situation where we split this block of memory into two chunks with quite a bit of waste, meaning that so here we have 29 kilobytes of memory and we're using 512, and then we have 480 kilobytes usable memory, meaning that this 29 kilobytes of memory will be practically wasted, since it's not big enough to do something meaningful, but it's not small enough to be ignored. So what we can do, another thing we can do, is we can relocate our bootloader, meaning that we can copy our bootloader from here, and so from this sector here to this sector here, to the start of this sector, so that we can have this memory here that being contiguous, and we can use it in a linear fashion. Other parts of the memory are not usable, so those are, we don't have to worry about those. But yeah, so it's something that we need to keep in mind. If we find ourselves needing memory, and I think we will need memory depending on how big our kernel is. So this is something that we might want to come back to and relocate our bootloader into a bit higher into memory so that we can have contiguous memory so that we can load stuff into it. Right, but for now, let's just say that we will set up the stack between 0x500 and 0x600, right? Okay, so let's do that. One thing to know is that stack grows up, meaning that if the stack will grow towards the lower address. So that means that what we need to do is we need to go to the stack pointer and set it to the higher address that we want our stack to basically the end of our stack in memory. So what we will have is something like this is stack end will be 0x500, and then stack start will be 0x600, and if we push something into the stack, this will be our current stack pointer, right? Something, so 5F0, for example, right? So we need to initialize both the base pointer, which is the stack start, this is the base pointer, and the stack pointer to start with to 0x600, since we don't have anything on the stack yet. So 600 move base pointer 0x, yeah, it doesn't like this, so let's just do it this way. We might also oh yeah, let's do something meaningful. Let's clear interrupts and clear the direction flag so that it's 0. By default, Box will initialize it to 0, but on actual hardware, it's not really a guarantee that you have. Let's also do a very few things since we're doing initialization. Let's set up a few registers, right? So let's set up AX to be 0. Let's set up our segments, okay? Let's move 0 to SS, and AX is 0. Let's also move into ES, since that's something that we will use for indexing. And let's also set our so what I want to do also is I want to set our data segment to be the same as the code segment, so that if we want to relocate our bootloader, it'd be easier, right? So let me just push the code segment and then pop it into the data segment. Okay, cool. And let's just add. I like to label everything because it makes keeping track of what we're doing much easier. So let's call this check disk, right? Okay, good. Like, I guess we can get rid of this because you can always go and look at the documentation to understand what we did. But for now, we're looking good, I think. So now we have a stack, which is cool, meaning that we can actually start using the stack for stuff. But before we do that, there's yet another ingredient that we need to know about, right? And that is the LBA. So what is or actually, what is the structure of the LBA packet? Because it's something that we want to use to talk to the disk. So let me just LBA packet structure, and this is something that we will want to have. Right. Okay. Cool. So let's come over here and take a look at this. So the format of this packet address is right. So offset 0 and size is 1. And this is the size of the packet, and the packet is always 16 bytes. Okay, which is yep. So offset 12 plus 4 is 16. That's fine. The offset one, the byte one, is always 0, I guess. And then the number of sectors to transfer with a maximum of 127 on some biases, but I don't think we have that issue. So offset 4, size 4 is the transfer buffer. So we will have it as 2 parts, a 16-bit segment and a 16-bit offset. And C not one we'll read in a bit. And then we have the lower 32 bits of the 48-bit starting LBA, and then the upper 16 bits of the 48-bit starting LBA. Okay. Actually, let me just copy this and set it as a, let's call this LBA packet struct. And I'll just use this as a bit of a guideline. Of course, this one. Cool. This one is a bit of a push. There we go. Right, so what we will need to do is virtual, and then we do add, and then we need some address, right? Yeah, we need to add it with and virtual, and we'll call it LBA. Actually, hold on. Let me just call it LBA packet, and we will define this LBA packet where it resides in a bit. So LBA packet. So the first one is the size, right? So this size here will be a D word, and its value is unknown. All right. Then what we have is okay. So what we did is what I did is I combined these two. So size of the packet is 16 bytes, right? Except this is just 1 byte, which means that this size here is split into 2. Okay, so 1 byte and 1 byte. And this one here is always 0, so it's fine. So that's why I defined it as a D word, because it's fine. Then we are at offset 2 because D word is 2, so 0, 1, 2. We are at offset 2, and this is the number of sectors to transfer. So let's call it sector count, or just count, right? That's fine. And then what we have here is, so we have the count as a D word, and here we have the transfer buffer, and this is split to segment and offset, and every one of those is a D word. So what I'll do is I'll split them into 2 also. So call this segment, and call this offset, right? So now we have the transfer buffers, and now we will need to have the addresses. Okay, so here every address is 4 bytes, except that we can't really handle 4 bytes because we are in real mode. So we will need to split the 4 bytes into 2 bytes. So what I will do is I will go ahead and do something like address. This will be 0, which will be the very low bytes. And this one, so we'll need 4 of those. This one will be 1, this one will be 2, and this will be 3. Actually, this is not the address, is it? This should be the sector. Yeah, this should be the sector because it's the LBA, it's the sector number that we are trying to read. Right, so this is the structure, and now we just need to put this LBA packet somewhere in memory. So again, let's take a look at the memory map. Where do we have free memory? I guess we have free memory here. So starting here is free, right? So we can just put it 7E000. All right, let's just do that. Let's set LBA packet to be equal to this address, right? And that means that we basically have defined a new variable at this address that has this structure. All right, let's do this. So what we need to do is, I guess, move to the world in LBA packet dot first one, I guess, is called size, and then we will just set as the size, which is 16. So this is fixed basically since the size of every packet is 16. Then we move the word in LBA packet dot count. We'll just read 1 for now, thank you. Then where do we want to read them? I guess let's look back at our memory map, right? So here we have our stack between 500 and 600. If we ever wanted to move our bootloader, we'd move it at 600, so it'll be between 600 and 6 FF, or let's just run it up to 700. That means that the memory we'll have available will start at 0x800. So let's start reading our sectors into 0x800, since we can do that. Right, let's go back. Okay, so let's move word. So hold on, let me just check. So we need the segment and offset. Okay, so we need the segment will be, so let's move it at LBA packet dot segment, and this will be, so this will be ATH. So this basically means that the segment will start at 0x80, and the offset will start at 000, which means that this will basically give us 0x800, right? And then move word LBA packet dot offset we just set as 0, as we just said. Okay, I guess that's about it, I think. Oh yeah, we forgot about the... so we have to specify the sectors that we want to read. And that's where it starts to get a bit dicey, because we want to read a sector where our second stage of our boot drive is bootloader is, but we don't know which sector that is, and we don't know how many sectors we need to read. For the moment, we just set it as 1. Read 1 sector for now. Needs to change when we have a second stage, right? So let's just read the second sector. We know that we are the first sector, since we were our bootloader was loaded from the first sector on the drive, right? So if we want to do something meaningful, we can just read the second sector. So let's set sector 0, I think I called it. Sector 0. So here I need to think a bit about how these things are laid out in memory. So sector 0 would be the lower word of this 32 bits, meaning that it should be fine, right? So we can set it to we can set it to the so let's say to 0. And that's, so basically what I was thinking about is sector 0 is comes before sector 1. So in memory it should look like something like this. Sector 0 and then sector 1, right? So sector 0 is effectively the high part of this. Whoops. Where was I? Yeah. So sector 0 is effectively the high part of this sector 32 bits of this D word. So this is a D word, right? Which is the lower 32 bits of the sector number. So this would be the high part of that D word, right? And this would be the low part. So if I want to read sector 2, I would basically set sector 0 to 0, since it's just 2, and sector 1 to 2, right? So I hope that's clear enough. So let's do that. And actually you don't need that. Just set that word to 2, that should be fine. And then I guess we just need to clear the those other sectors, right? So set word LBA packet sector actually 2 to 0, and it should be sector 3 to 0. Right. And then it's as easy as we need to set up our int 13 call, and I'll just go ahead and copy the parameters and results that we are expecting here to our code, just so we can see them. Right, let me just do something like this, this, and this. There we go. Cool. So these are the results, and these are the inputs. All right. Okay, cool. So what we need to do is, yeah, actually, no, it's not. Yeah, there we go. Oops, results. There we go, right. Okay, so what we need to do is we need to set AH to 43H, right? I'm looking at this one here, and then AL needs to be, so bit 0 is close write check, open write check. We don't really care about any of these. We don't really care about any of this. DL needs to have the drive index. I think it already has drive index. We didn't touch DL here. Yeah, we didn't touch DL, so it already has the drive index. That's cool. And then DSSI need to be the segment and offset pointer to the basically the structure that we've just created, right? So DS is the same as CS. We've initialized it. It should be 0. So we just need to initialize SI then. So move SI, and what do we put in SI? We put it the address of the LBA packet that we've created. That's it, I guess. We just go ahead and call int 13. And with this, we are done with this setup part on the inputs. So we just need the results to do the check. And let's do the check. Let's move. So what do we need to check? Actually, let's just check this. If it's set on error and we have the error code, but we don't really care. So if it's, so jump if carry. So if the carry is set, we'll jump to sector read error. Read error, if I can type. And we'll just put that here. Read error. And that will do move SI sector read error, and it will jump to panic func, right? So let me just copy this, go here and do it like this. And what's a good error message here? Couldn't let's, yeah, cool. Couldn't read sector from drive. From drive. Okay, cool. So with this, we should have, so here we actually, let's invert it, okay? Let's invert this, and let's just, instead of doing this, let's just do a jump if not carry. So if everything goes fine, we'll jump to read success. Okay, so here we can do stuff with the data we just read instead of just going back and forth and jumping to the error, right? So if the carry is set, we'll just continue straight on to this jump here that goes to the panic function. Right, so then we have the read success. So this is where we need to pause for a bit and think about how we are going to do things. So what we need to do is So basically here, let me just summarize. So summary, we have read something, something from disk. We don't know what it is. So we don't know what it is. Basically, we don't know if it's our second stage or not. So we need some way to ensure to validate that what we read is actually our second stage, and then we will just jump to the second stage, and then we'll be done with this first stage of the bootloader, right? So how can we do that? I guess one way to do it, one way that would be very easy, I guess, to do it is to have a sort of magic number, something that we know for sure that is unique to our second stage, and we can check for that magic number as soon as we load that second stage. And actually, it's something that's that is used by a lot of bootloaders. We will add a variable or a constant, I guess. Just call it constants. They're not really variable, are they? Actually, they are variables. Since we are setting this boot drive here. All right, fine. Right, so let's have this called magic bytes. And this will be a set of bytes. And what will be good bytes? Let's let's do this. So F4H and so F1CH. Yeah, let's just use that. So fuck. So these will be our magic bytes, and actually, yeah, I actually forgot to do this. I'm surprised it actually compiled. All right, fine. Okay. So we have our magic bytes. So we just need to basically check that we actually have them all when we read our code. When we basically read our sector, we need to check that actually the very first 2 bytes are the magic bytes, right? Okay, so let's move into what's a register that we're not using? I guess BX is not used. So let's move BX, the address of magic bytes, and then what we will need to do is we will compare the so the word in all right, so this is something else that we need to do. So we know that we've loaded our segment at 80H, but is that something that we want to hard code? I don't know. So let's just let's you know what? Just do with it for now. So the word in that address, let's move CX. Do we use CX for anything here? It should be fine, right? So let's move 800 to CX, and then the word in CX, we compare it with BX, right? So it's 2 bytes. And if we, so jump if not equal, and here we'll need to do an error, not sector 2. Okay, so let's just add that, not sector 2. Yeah, of course. And same thing here, remove SI, not valid magic. Let's use proper grammar. So, and then call jump to the panic funk. Right, let's call this bad magic. Bad magic. Right, so we fail if we don't find it, but if we do, then that means that we need to hand off our execution to that stage. And we know that the first 2 bytes will be magic bytes. That means that the first meaningful instruction will be at the address 0x802, right? Which is 2 bytes, which is the address where we loaded our sector plus the 2 bytes that are magic, right? So let's move AX 0. Actually, you don't need to do that. I just need to do this and 002H. So for now, we have the correct address, the first meaningful instruction of the second sector in AX. So the final instruction we need to do is jump AX. And with that, we are done with the first stage of the bootloader. Great, let's see if it still builds. It does not. Use of reserved. And why is that? Wait, what? Okay. So it's still failing because it doesn't like CX to be used as a okay, so maybe word pointer. That would be better. It does not like it used this way. Okay. I guess the issue is with CX, right? Okay, so I can solve this pretty easily. Move word, right, something like this, something like that, and it should be fine. Yep. So now we have a different error, which is the symbol is not defined. Read error. Oh, of course. Success, right? Okay. Invalid magic. Of course. We haven't defined that, have we? So let's copy that. Go all the way here. And invalid magic would be something like invalid red sector doesn't start with the expected magic bytes. Something like this, okay? All right, let's build. Yes! All right, we are building. We are still confined within the 512 bytes that we need to use, so we're still just taking one sector. Let's also do something very cool. Let's look at what our bootloader looks like. Okay. It looks like we still have quite a bit of space, so yeah, quite a few bytes that are left over. And this is what we look like. We are setting. This is us setting up the packet, and then we call the packet here. Actually, hold on. Did I? Okay, nice. Wait. Oh shit! Actually, I just got an error. I think I've copied the wrong. I have copied the wrong value here because I'm using 43, and 43 is for writes. So let me just go ahead and double check what needs to be changed. Oh yeah, okay. I was looking at 43 actually. 42. So 42 AH needs to be 42. Let's go back and set that. So AH needs to be 42. Let's go back and set that. Then DL, okay, DL is fine. Then, oh, actually, okay, fine. We have the size. This is a new, it should be 0, so that's cool. So the offset must be declared before the segment. So that's something that we need to look into. Surely that's something that we've messed up, right? Yeah. So the offset needs to be declared before the segment, since it's a little Indian. And that being said, I don't think anything changes here because we're still pointing to the correct offsets in memory, so it should be fine, right? Yeah, all right, fine. So CF set on error clear, if not no error, that should be fine. It's what we had already. And as that the complete buffer is inside the given segment. Okay, that's fine. We don't really have that issue since we're only reading one segment for now. I guess that should be fine. So let's just rebuild it and re-dump it. Okay, so let's look at this again. So here we are saving our boot drive into our boot drive variable. We've never ended up using it, but we'll see if we'll need it if DL gets overridden by some operation we've done afterward. Right, here we set up the packet. We call 42. SI is the address where we put our packet, and then we call the interrupt. Then jump. Okay, so we jump all the way here, where we check. We move the magic bytes to BX. We compare. We move the bytes that we've loaded, the first 2 bytes, to CX. We compare BX and CX. If they're not equal, we go to the error. Otherwise, we load we load 802 in AX and we jump there. it should be fine, I guess. Yeah, it should be fine. All right, so let's try to do something. Okay, let's try to do box. Let's have it start. Okay, cool. So this is what I was talking about before. Since we are still booting from a floppy, we are getting the panic message which says that the hard drive doesn't support LBA packet structure, which is fine. So in the next installment, we'll be writing utilities to basically make the creation of disk images easier and try to make the process of writing the bootloader on the first sector of the hard drive more streamlined, as well as actually having a partition structure on the hard drive. All right, until next time, take care, bye.